the 5 types of arithmetic that are up here on the screen, which ones of them have we already seen how to work with? So we've seen some multiplication and division this semester already. Addition and subtraction, we haven't yet. The way that our units are set up, nothing in unit number 1 this semester required you to add or subtract fractions one from another. But there was a couple of instances in which you may have had to multiply or divide, so that's why it's set up the way that it's set up. So let's start with the multiplication and division because that's stuff that we've already talked about, and then we'll take our step forward into addition, subtraction, and exponents. So what's the easiest one on the screen of these 5 to do? The one that requires the least thought. You would think it would be adding, because in a way addition is the simplest operation in arithmetic, right? It's the one on which all the others are built, right? So usually addition is the easiest thing to do. Unfortunately for fractions it's not, for reasons that we'll hopefully see in a minute. See, I would go to multiplication. So tell me, if I were to multiply 5 6 times 1/9, what would I do? What's my process? 5 times 1 and 6 times 9. So remember, when you multiply fractions, you multiply not cross, but across, right? So we're going to multiply straight across the numerator and straight across the denominator. 5 times 1. So I'll get 5. And then straight across the denominator, 6 times 9. 6 times 9 is... this is where my brain is at this afternoon. I'm having trouble with two-digit. Never let it be said that I can't sympathize with you guys on this kind of stuff. Yeah, my brain's addled today. Thank you, 54. So right, most important thing about multiplication is you multiply straight across, right? Numerators times numerators, denominators times denominators. And then the only step that remains would be to ask, can I write that fraction, 5 over 54, in a simpler form, in lower terms? How do you know, Joe? Right, so what would we reduce the numerator and denominator by? The only options upstairs would be to divide by 5 or to divide by 1. Dividing by 1 is not interesting, so dividing by 5. But we can't divide 54 by 5 and get a whole number. And so this fraction is in its lowest terms, and we're done. So that's for multiplication. Simplest one because it's a single step. Just go straight across the numerator, straight across the denominator. How about division? What's the difference if I want to divide these two fractions instead of multiply? What do I have to do? Right, so we can look at it in 2 different ways. The way that's a little bit dangerous is the way that you just said, and I'm okay if this is the way you do it, but I'm going to hope to convince you that it's a little bit dangerous. So what you just said is to not do the across multiplication, but do the cross products. 5 multiplied by 9 and 6 multiplied by 1. That's the way that I'm going to recommend. Yeah. So the first way to look at it is as a cross multiplication, but the way that I prefer is to turn this division problem into a multiplication problem by replacing the second fraction here by its reciprocal. Now I'm even having spelling issues today. I need a neurological exam when I get done today. So right, take the reciprocal of the second fraction. And what does reciprocal mean? You said what it was, but just to say a little bit louder, what do I do with this second fraction?
Just invert.
Invert it, yeah. Exactly. So the old numerator becomes a new denominator and vice versa. So I'll flip it upside down. Sometimes you just call it flipping, but the math term for it is reciprocal. We're replacing that number by its multiplicative inverse. And that has the function of trading out. So we no longer want a division sign here. What do we want? A multiplication sign. So not only do we flip the second fraction, we change the nature of the arithmetic. We invert the fraction and we invert the operation. So now I've turned it into a multiplication problem, and now that it's a multiplication problem, we know what to do with it, which is multiply straight across. Right? So the 5 times the 9 and the 6 times the 1 gives me 45 over 6. And then we just have to ask, can I reduce that fraction into lower terms? What do you think for 45 over 6? Let's list some factors. So 6 has a 2 and a 3. What are some factors of 45? 5 and 9, yeah. And 9, on the other hand, is... So if we play the greatest common divisor game with 45 and 6, what's their greatest common divisor? 3. They both have this factor of 3 in common, one to another. So in fact, both are divisible by 3, and I can reduce this fraction. Divide by 3, divide by 3. So downstairs, 6 divided by 3 is 2. Upstairs, 45 divided by 3, 15. And 15 over 2 is evidently in lowest terms, because the only thing we could divide by to satisfy the denominator is 2, but we can't divide 15 by 2 evenly. And so then we're done. So we know how to multiply, go straight across. We know how to divide. Replace the second fraction with the reciprocal, and then multiply across. What's the one fraction step that we didn't do in either of these two examples? I'm hoping that's a careful enough question that you'll know what I'm talking about. When we multiply or divide fractions, we do not need those fractions to have common denominators. Common denominators. Okay, I ran out of room. No need for common denominators if we're multiplying or dividing. And that's good news, right? You can find common denominators and work with them if you want, but you don't have to. In fact, in a lot of ways, it makes things more difficult when we're multiplying or dividing, because if I find common denominators, my numbers in the numerator and denominator tend to get bigger. And then if I then have to multiply those bigger numbers, we're going to get even bigger numbers. And then I'll have to reduce those fractions, and I'm starting with an even bigger fraction to reduce. So it's not wrong, it just gives you more work to do, right? It's going up over the top of a mountain instead of just taking the path around the side. Because we don't have to when we multiply or divide. But common denominators are a part of everybody's vocabulary. They're imprinted upon everybody's brain who's taken an arithmetic or an algebra class, because they are necessary to do when? When adding or subtracting, right? So those are the times when we do need common denominators. Always. Always, always, always. And by the way, common denominators. Everything that we talk about today with fractions that have just numbers in the numerator and denominator, we're also going to export that knowledge to how we work with variable expressions that are in the form of one thing divided by another thing. So we're going to see all this fraction arithmetic stay with us in the form of working with what are called rational expressions later on down the line. So second or third week in March, we're going to get to do this same stuff, just with variables in play as well. But the same rules still apply. Multiplication and division don't need common denominators. Addition and subtraction do. Exactly. Right. So remember, when you raise something to a power, it's the same as multiplying it by itself. So we can rewrite this as 5/6 times 5/6 times 5/6. But when we write it that way, now that it's a multiplication problem, how do we know to multiply fractions? Just multiply them straight across. And I want to pause and insert my intermediate step here to note that what we really have is 5 times 5 times 5 upstairs and 6 times 6 times 6 downstairs. In other words, what we really did is we really just, as you said, applied that exponent to the numerator and we applied that exponent to the denominator. So that's part of the good news, is that that exponent outside can be distributed to the numerator and to the denominator separately. 5 raised to the third power and 6 raised to the third power. And then all we have to do is evaluate those. 125 over 216. And then we're done. So that's how we can handle raising a fraction to a power, to a whole number power at least. So we talked a little bit before I gave you the chance to work on this about the need for common denominators when adding or subtracting fractions. And so in an example like the one that's on the screen, finding a common denominator is actually our first step in such a process. But let's imagine just for a moment that I change the problem just a little bit. So if I start out with two fractions whose denominators are identical, then what? What if I already have common denominators? How do I add two fractions?
Just add the denominator.
Add across, yeah. Add across the numerator, and the denominator becomes the same, right? So notably, when we're adding or subtracting fractions, the denominators at the addition and subtraction step never change. Denominators were 9s to begin with, and the denominator remained a 9 at the end of the day, right? It's going to change probably now if we simplify this fraction into its lowest terms. What are lowest terms for 6 over 9, by the way? 2/3. Dividing both sides by 3, we get 2/3. But the denominator at the addition step doesn't change, so we don't get 18 here. That's a common error, right? So 6 over 9, we added the numerators, kept the denominators the same. So we know what to do when our fractions have common denominators. So if our fractions don't begin with common denominators, all we have to do is somehow get there. Right? We have to get to this stage, because once we get to this stage, we know how to handle it. So let's look at the original problem, 5/6 plus 1/9. What I'm looking for is a way to put these two fractions on the same footing. Call them denominators as if they're like denominations of dollar bills. I use this analogy a lot, right? I can't stack 5 $1 bills along with one $5 bill into one giant stack and say that I have 6 of anything, right? I say I have 6 bills, but I can't say that I have 6 1s. I can't say that I have 6 5s. I can't say that I have 6 of anything consistent, right? So before I add two fractions, they need to be in the same currency, the same types of bills. So before I add together a $5 bill and a bunch of $1 bills, I should change out the 5 for a bunch of 1s. So then I have a bunch of 1s to count, right? So that's my currency analogy that I'd use way too much. So to do that in this case, I need to find a number which I can put in the denominators of both of these fractions that's the same as one another. But I need to do so in a way that makes each of these two fractions have the same value as the original rational number which appeared here at the beginning of the line. So whatever fraction I put here has to be numerically the same number as 5 over 6. And this one has to be the same number as 1 over 9. So somebody give me a way forward here. What can I do to decide on what, first of all, would be a reasonable common denominator for these two fractions? 18. So I agree that 18 is a good choice. But why is 18 a good choice? Or how did you come up with the number 18? What's your thinking there?
3.
Okay, so 18 is two things. It's a multiple of 6, because it's 6 times 3. But notably, it's also a multiple of 9. It's 9 times 2. So the fact that 18 works at all, it only works because it's what we call a common multiple. It's a common multiple of 6 and 9. If you're ever at a loss for how to proceed, you could always, and some books actually recommend doing this, it's probably not something you do very often, but you could start just by listing multiples of 6. These are things that you might have off the top of your head. And then also listing multiples of 9. 36... 45. Let's do one more. 54. Right? So you could list a bunch of multiples of 6 and a bunch of multiples of 9, and then you just look for the commonalities. And in general, there's going to be a lot of commonalities that we could use, and any one of them is good enough to get us to progress, right, in our problem. But you chose 18, not only because it's a common multiple, but also because it's the least. Exactly. It's the smallest number, which is both a multiple of 6 and a multiple of 9. By the way, fun fact from number theory, one of the reasons we know that it's the lowest common multiple is because this number 3 and this number 2 have no factors in common. So one of the ways to tell that we've found the least common multiple is that cofactor which separates each of our numbers from that multiple, those cofactors have no factors themselves in common. So this 3 and this 2, nothing in common. That's why 18 we know is going to be the least common multiple. Using the least common multiple here is nice because it's going to give us the smallest numbers to work with in our fractions. In general, though, and this is a piece of advice that we can follow now if we want to, or we can use the least common multiple, but later on in the course, it might be advantageous to do this instead. One of the things I like to recommend is we don't always have to use the least common multiple for this purpose. Any common multiple at all will suffice to move us forward and get us common denominators. So one of the tricks that you can do, it's not really a trick, I mean it works every time, one of the things you can do is just go ahead and multiply the two denominators together, 6 times 9. And so that's going to give me 54, which is definitely a common multiple of 6 and of 9, right? And so we can go forward in this problem in just the same way. We just had to do a little bit less thinking at this stage, right? We didn't have to think, well, what are the multiples of 6? What are the multiples of 9? Let's just multiply the two of them together. We're always guaranteed to get a common multiple. It's not necessarily the least common multiple, but it gets us a step closer to our goal. So if you're stuck and you don't like thinking about least common multiples, just multiply the two darn denominators and get on with it. Right? One of the other benefits of this is what happens in the next step. And so I want to actually revisit this tactic in a moment. I want to go back to your least common multiple way of doing it one more time. So when we were using 18 as our denominator, we need to decide now how to change the numerators of these fractions in a way that preserves the value of the original fraction, right? We can't just change the denominator of a fraction in just any way we want to, right? Because in general, changing the denominator of a fraction is going to change its value. If I have the same amount of pizza, but now 3 times as many people show up to eat it, guess what? Each person's getting a third of the amount that they would otherwise have gotten, right? That's how fractions work. If I triple the denominator, then the value of that fraction goes down by a factor of 3. If I triple the numerator, the value of that fraction goes up by a factor of 3. So whatever we do to a denominator of a fraction also has to be offset by a change in the numerator. So I guess what I'm really getting at is if I'm going to multiply this 6 by 3 and get 18, what else do I have to do to make sure that this fraction still has the same value, 5 over 6?
Multiply the 5 by 3.
Exactly. So every change that we do to a denominator has to be offset by the same exact change in the numerator. So if I multiply the denominator by 3, I also need to multiply the numerator by 3. Otherwise, we have a different fraction, and we can't have that. Right? We need to keep the same fraction at this stage, because we want to be able to add together two things that have the same denominator, but which represent the same quantities that the original fractions did. So when I multiply the denominator by 3, I do the same thing with the numerator. Likewise, what should I do to the numerator of the second fraction? Multiply by 2, because that's what I did to the denominator of the second fraction. So now I'm going to get 1 times 2, that's 2 over 18. So this was the step. This was the new step when we talk about adding and subtracting fractions that we don't have to worry about when we're multiplying or dividing. Find that common denominator, any common denominator. Right now on the screen we have the least common denominator, but any common denominator will work. And now that the denominators are common, how do we add these two? Yeah, just go straight, add across the top. 15 plus 2 gives me 17. And the denominator remains the same. And since 17 and 18 have no common factors, we stop. We're done. That fraction is in its lowest terms. So adding fractions together is a two-step process of first discovering what the common denominator is, and balancing out the numerators in the same way that the denominators balance. Right? Whatever happens on top happens on bottom, and vice versa. And then once the denominators are common, all we have to do is add across the numerator. Let's go back to the world in which instead of finding the lowest common denominator, the lowest common multiple rather, we decide to just go ahead and multiply 6 times 9. Any common denominator works, so why not try this one? Well, what's the benefit of this one? Let's take a look at what the first fraction would become if the denominator turns from 6 into 54. What do I have to multiply by to go from 6 to 54?
5 times 9.
Times 9. But the thing about multiplying by 9 is that the number 9 also happens to show up right there in the other fraction. So what do I need to do with this 5? As Greg just said, I need to multiply that 5 by 9, which I can see is just writing 5 times 9 like this. But another way to see it, and again, this is a little bit dangerous if you don't remember what you're doing, but another way to see it is that that new numerator is just going to be the cross product of this 5 with that 9. So I kind of like this method because it, to me at least, has what we call a lower cognitive load. We do less thinking when it comes to this method. At least we do less thinking up front when it comes to the step that people screw up the most, which is finding and balancing common denominators. So if that works for the first fraction, how do I find the numerator for the second fraction? What do I have to multiply 9 by to get 54? that's 6. And 6 happens to be the other denominator. Right? So my second numerator I can find just as the cross product of this 6 and this 1. So this is kind of a way, again, to bypass some of the difficult cognitive work of balancing out a common denominator. As such, you might decide to do it this way, you might decide to do it the original way. Either which way you do it, it ends the same way, right? We add the numerators together. We keep the denominators the same. But now it seems like we got a different answer. So how do we resolve that? This whole method that I just showed you is worthless if it's going to get me a different answer than the answer that we got before, which we believe to be correct. So how do we navigate that difference? What's 51 over 54? What are some of the factors of those numbers? These are numbers we might not factor very often. 3. Oh, is 3 a factor of both?
Yes.
I think it is. By the way, does everybody know what the trick is to tell when a number is divisible by 3?
You like add them up, so 5 plus 1.
Yeah. So you add the divisibility by 3 trick is you add together the digits of the numbers. So 5 plus 1. That gives me 6, and what do I do with that? How do I...
See if it's divisible by 3.
Yeah. So 6 is divisible by 3. And the trick is that that also means that 51 is divisible by 3. Check it for 54 as well. 5 plus 4 gives me 9, which is divisible by 3. So this is a little trick to how to tell whether any number is divisible by 3. Add up the digits. If the sum of the digits is a multiple of 3, then the original number is a multiple of 3. It's a neat, really neat little way of telling. So we know that we can divide both of these by 3. And when I divide 51 by 3, I get 17. When I divide 54 by 3, I get 18. So in fact, we have the same answer that we had in the first place. So choosing the least common divisor, the least common multiple, gives me a little bit more work up front. And then it saves me the step that we had to do at the end, which was the reduction step, right? Doing it this way, finding the common denominator just by multiplying the denominator straight across, gave us less work in the beginning, right? And instead, we had to invest our effort into the last step, which was reducing the fraction. Because just multiplying across the denominators is always going to give me something that's at least as large, if not larger, as it was in this case, than the lowest common multiple. So if you're okay with that, this method works great, and then you just have some reduction to do at the end. If you prefer to work with the least common multiple instead, then you can. You'll just do the work up front instead of at the end. So it's a little bit of a push. Whichever way is more comfortable for you is the way that you should probably stick with.